Hello everybody. In this particular lecture, we will consider effect of zeros on the system response, and I will not really worry now about, well, let me, with an abuse of terminology, call it a stable zero. We would be mostly interested in zeros on the right half plane. What about the zeros on the left half plane? We had done several analysis on that in module 7 and even through other design procedure in module 8 and 9. So we know what is the effect now of a zero on the left half plane, how it helps improving the transient response, and so on, right? But so far we have not really discussed about in detail about zeros. We talked about zeros only when we were facing some problems in the design or in the performance specifications. All we were interested, even while drawing the root locus, was how my poles change as the gain varies from 0 to infinity. Similarly, even while we were doing the Bode plot, we never really worried much about what is the role of zeros and what are the implications of having different kinds of zeros. So in this, I just start with some basic things, right? So what is a mathematical zero? So if we go back to history a little bit, well, there was no symbol for zero, right? If you remember what we learn in Roman numerals in school, there was no concept of zero there. You had x, v, then l, and a c. I don't even know why we are forced to learn those things, even though we had a much better number system, right? So, and there's a few other things, other civilizations where they had some kind of symbol for zero, and first day of each Mayan month was zero. But significant advances happened in through Indian mathematics. So the zero invented here went through the Arabic world and then to the west through Europe and so on. So if you typically ask a European who invented zero, they would actually think it's actually an Arabic number system, because that's where they imported it from. But it's the biggest contribution of Indian mathematics. Okay, so we'll not discuss about the Indian mathematics here. What we will look at is the role of zeros in our context, in the context of control systems. So far in our analysis, even when we started with poles or started with the analyzing stability, everything was depending on pole, zeta, omega n, everything, and the characteristic equation, everything came in the denominator. And for a system of the form, now these are what is referred to as state space equations. Okay, this will come up in detail in module 12, but for the moment assume that we have our system in a differential equation form of this way, where x dot are my states, A is the system matrix, B is the input matrix, Y is an output vector, and C is the output matrix. So typically what this would mean is, well, I have x as an n-dimensional state vector. It could be x1 till xn, it's a transpose. A is an n cross n matrix. Okay. Similarly, B, if there is just one input, would just be an n cross 1 matrix. C, if there is only one output, so one input, one output, means u and y are simply scalars, and C would then be 1 cross n matrix. In some cases there could be D also here. And okay, so how do I go from here to here? The way I go from here till here is, so I just take the Laplace of this, as x of s is A x of s plus B u of s, and then y of s is C times x of s. And then I keep eliminating things, and what I find is, I'll skip the steps here, but this should be very straightforward to find out. So this would be so C x of s comes from here, this would be Si minus A inverse times B. Okay, so you can just eliminate x of s from here. So this will be Si minus A inverse x of s is B times u of s, and then you could do the manipulations. So this is what we call as the system in the state space form, and we had discussed this very briefly in one of our first lectures. Of course, we have not analyzed much on what is the nature of A, B and C. That will come in detail later, but from here to here is a very straightforward procedure. You just take the Laplace transforms and take the ratio of y over u, and if you have a d here, the d will very plainly just sit here. Okay, so you are eliminating x from this equation and just substituting for here. Sorry, this is some error here. So this would not be an inverse, this would be plus here, and when I do it on the other side, x of s would be si minus a inverse times b u of s. Okay, and then it's a little straightforward. So this is a, sorry, I just made a mistake here. This should be a plus 1. Okay. So now this is also what this is our transfer function, and if you look at it carefully, what goes in the denominator is this si minus a inverse, right? So you have this the way you compute the inverse of a matrix, you take the determinant and then you take the adjoint and so on. So the determinant or the denominator here will only depend on what is si minus a inverse. I am not talking anything about c, b or even d at the moment. The poles determine whether a system is stable or not. Okay, in addition to the decay rate and oscillation frequencies of the initial condition response, right? So it talks about stability, it also talks about the transients, the decay rate, the frequency of the oscillation in terms of omega d. Decay rate is determined by zeta, and what is important to note here is, while I do this analysis, is that the poles do not depend on b or c. Therefore, instead of this having this, if I just say I want to analyze x dot equal to ax, the autonomous system, the characteristic equation will just give me the poles si minus a equal to 0. It is the same thing, right? So I do not really worry about what is b, c and even d for that matter. So the message from this slide is that the poles only depend on the A matrix, okay, just because of this guy, and they have nothing to do with B, C or even T. Okay, now zeros are determined by the system matrix A as well as the input B and the output C. Now what does this inputs suggest and what does this output suggest? The input matrix, or the way the input enters to the system, is via placement of certain actuators, actuating elements. Similarly, y are the measurements which we will or the y's are the quantities which we will measure physically, and therefore y comes through some sensors, and y's will determine, or the c will determine where my sensors are placed. So these zeros are determined by the system matrix A as well as the input matrix B and output matrix C. Practically, what do they mean? Practically, the zeros depend on the physical placements of the sensors and actuators relative to the underlying dynamics. Okay, now this is what distinguishes a control system from a standard dynamical systems emanating from physics. So the concept of zero is what distinguishes control theory from dynamical systems theory, and of course throughout this, so most of the analysis we will do is for strictly proper transfer functions. Okay, let us see this with some very simple example. So I have A as 0, 1, minus 1, 0, say B is 0, 1, C is also 0, 1, and say D equal to 0. Then I do the math, C Si minus A inverse B, D is 0. So what I get as a transfer function G of S is S over S square plus 1. Okay. Now I keep all this same. So A does not change, B does not change, C does not change, D does, and say I put D equal to 1. Then what I get as a transfer function G of S is S square plus S plus 1 over S square plus 1. You see, nothing changes in the denominator, the poles are the same. What changes from here till here is the location of the zeros. There is one more 0 added here, and you could similarly take, maybe B as 1 0, C as 0, C as 1 0, and you will get different numerators for each of them. So the zeros are determined by not only A but also B, C and in also many cases t. Okay. Okay, so what do exactly these zeros do, right? So 0 of a transfer function is the root of the numerator polynomial of the transfer function, and it can be a real or a complex number, or just be as the number 0 also. Then when the transfer function is asymptotically stable, so in this analysis we will only be interested in transfer functions which are asymptotically stable, which means all the poles are to the left half plane, and each 0 then has a specific effect on the asymptotic response of the transfer function for certain inputs, and this is what we will do throughout this lecture. Okay. So let's just revisit the slides which we had last time. Okay, so what we will in this lecture typically be interested is in non-minimum zeros, where the zeros in the right half plane. Okay, so what we discussed last time about all these things, how do I distinguish between minimum phase and non-minimum phase via the Bode plot? We also concluded that if the system is minimum phase, the magnitude response will uniquely determine the transfer function. And well, okay, so there is things like we said, and we will actually detail this a little more, that non-minimum phase systems are slow in response because of the faulty behavior at the start of the response. A common example is transport lag. So let's say I have a very simple example, right? I have a plant here, G, I have a controller, and well, maybe some reference signal, and as usual some output here, there is some input to the plant, and I say, well, there is a little delay between the time the control signal is sent and so the controller sends a signal to the actuator, and the actuator generates a control signal, and this is modeled in transfer function as e power minus s tau, assuming tau is the delay, and this actually comes from the Laplace transform of a delay signal. Ft minus tau is e power minus s tau f of s. Okay, this is a straightforward derivation, we will not go into the details of that. But why do I say that this system has or it will be faulty behavior at the start of the response? Now, what is the contribution of this delay here? That in the numerator it adds up e power minus s tau, and then you have c, g of s and c of s. And if I take a small approximation of this, this would just be e power s tau can be approximated at 1 over s tau, and then you have g of s, c of s. Okay. Now what this, and this is not a very elaborate proof, but just a very small evidence of what happens when I do this. So when I have a transportation delay or a transportation lag. So this is a system. So what is the nature of this? Now this introduces a 0 in the right half plane. Okay, and this will result in a system which is now non-minimum phase. Okay, so we will see what is the role of this 0 on the right half plane, how is it related to a transported lag? Well, it is related via this relation, and what is the faulty behavior here that we are talking of, right? So we will talk of these 2 points also, right? So non-minimum phase situation arises when the system has a non-minimum phase element or a minor loop inside the system which is internally unstable. Okay, so let's first talk of internal stability, and what does it mean? Mathematically, a 0 can cancel a pole when there are 2 transfer functions in cascade. Let's loosely speaking, say I have 1 over s plus 1 and there is a cascade s plus 1, right? So mathematically they will cancel each other, and this is 1. Okay, now we will not worry about how can I realize this and so on. That's not the worry at the moment. Similarly, when I have unstable things, this is s minus 1, this is s minus 1, they will also cancel each other, and I will have 1, right? So first is, okay, is this a stable realization? So if I say I have a unstable plant, I want to track a reference, say some r of s, so maybe capital R, and the input here, so okay, this is s minus 1 and then this is the output. Okay, then each time I could say that, well, I have an unstable plant here, unstable pole, cancel it with unstable 0 and I will get output which is exactly the reference I want to track. This is straightforward, right, just looking at it mathematically. But is it practically feasible? Well, it may not be allowed practically, because if this changes by even a very small number, say by 1 millionth for example, then, well, there is some instability here, there is no cancellation. Moreover, what if the initial conditions are not 0? Then you can never do this, because the signal from here till here is unstable, right. So, we'll talk of this when we will talk of unbounded internal signals. So, even if there is no discrepancy between these numbers, there could be an unbounded internal signal. Okay, what does that mean? So, if I take a configuration like this, right, say I have a standard reference, I have the output, the error, unstable pole here, and I have a 0 on the right and I have s plus 1 here. So, overall if I just look at the cancellation, right, so the system might look stable. Not only that, how does the error go? So, what we are worried about in the system is usually the error, and all the analysis in the transients or the steadies, sorry, all the steady state analysis we were doing in terms of this error signal. Okay. Now, this error signal or a transfer function from R to E looked something like this, which looked nice, right? This is actually stable. Okay. However, if I look at the transfer function from R to U, well, I have something strange. I have a s minus 1 here. Okay. Now, this is unstable and this is not allowed, right. So, there is some amount of hidden instability in the system. So, the signal from here to here, so the u which goes to this plant, if I may say so, is actually unstable, right. So, this u would be unbounded, and therefore, I cannot do much about this. This system is system which has a instability hidden within the system, right. So, now what do we do, right, in these cases? Well, therefore, to determine stability, it is necessary to determine the stability of all the transfer functions within the system. So, even when there is a perfect cancellation, we should not just blindly say, oh, the unstable pole is cancelled by a 0 on the right of plane, so system is stable. No. So, even so, with the arguments in the previous slide, we just cannot do this. A non-minimum phase controller 0 cannot be used to cancel an unstable plant pole, and in the same way, an unstable controller pole cannot be used to cancel a non-minimum phase 0. Either ways, right? So, so this is, we have to be very careful of these cancellations. Okay, second thing, what happens with these zeros? Again, we are just talking of zeros in the RH plane, right of plane. Okay. Now, say I just look at, say, a very simple transfer function of the form, say, s minus 1, s plus 2. Okay. And I just want to plot the root locus of this. So, I have a pole here and at minus 2 and a 0 here at plus 1. So, what happens as the gain k increases? Well, I go here, and as gain k goes to infinity, I am in the unstable region in the s plane of the sigma and j omega axis. So, these non-minimum phase zeros also limit the closed loop performance. Well, how do I do this? Well, my root locus plot tells me that as the loop gain is increased, the poles move towards the zeros, right? And then once I cross this line here, I am already in the unstable region, and therefore, whenever I have a 0 in the right half plane, my gain margin would be limited. And if the gain margin is limited, it would imply that the system has lesser robust stability properties. Contrast this with this case, right, where we had a transfer function of s over s plus 1, a pole here, it was stable for all case, no matter what you do. Okay. So, this is the effect also of a right half 0, where it where it introduces some additional performance limitations. Okay. Now, is that all? That a right half 0 does. There are some more interesting things which a right half 0 does. Okay. So, while doing the rest of the analysis, we will not do proofs. Some of the proofs are still open problems, but we will just try to understand the several phenomena associated with it and try to relate with what we had already studied in the earlier lectures. Okay. So, the first effect is what is called as a blocking effect of a 0. Okay. So, let us take a simple example here where the number 0 is a 0 of the transfer function, which means g of 0 is equal to 0, then the steady state response of it is also 0, and which means the DC gain is also 0, right. So, the steady state is the DC gain. So, for example, if I take this plant here and I say, well, what is this response? Well, the response initially goes up and it just goes back to 0. This is when I have g of 0 equal to 0. However, what am I tracking? I am tracking is a step input. Okay, so, this is a step response of a system which has a 0 at this number 0. Okay. Okay, next, what happens when I have a sinusoidal input? Say input of the form input in such a way that the frequencies of or if the input is sinusoidal with some frequency omega, okay, and then if the imaginary number j omega is a 0, of course minus j omega will be also a 0. If these two omegas are the same, okay, so in this, right, so I have roots at plus minus j omega or just plus minus j1. So, if I have an input of the form sin t, which has a Laplace transform of 1 over s square plus 1, then typically what we would assume or what we had learnt earlier, that if the input is a sinusoidal signal, the output for a linear time invariant system will also be a sinusoidal signal. What will change? Well, the magnitude will change, frequency will remain the same, and there might be a bit of phase shift depending on what are the components sitting in my plant or in my process. But that is not always true. Now, this something strange will happen here is if I subject this plant to a sinusoidal thing, which means I am essentially multiplying it with 1 over s square plus 1, this guy goes away and what remains is just the impulse response of this signal, which is stable, right. I just recover back, or I just start from 0, reach a peak and then go back to 0. So, the output is not a sinusoid for this case at least, and the condition is what, that this omega must be equal to this omega. If this is s square plus 2, then something else might happen, you might actually see a sinusoidal signal at the output. Okay. So, this is also, so these two were called blocking effect of zeros. Okay. Now, something even stranger, when we talked about stability. So, one of the first ways, so how was stability defined? Stability was defined in a way that if my plant is, or if my system is subject to an initial condition, will it come back to its rest state? From physics it will be, will it come back to its point of minimum potential energy, right. So, that is how we defined as stability, Another notion of stability was bounded inputs leading to bounded outputs, okay. And this analysis of bounded inputs leading to bounded outputs helped us characterize stability in terms of the location of poles of the system. Okay, but we never talked about what happens when the input is unbounded. If it gets me an unbounded output, is the system stable? Well, I do not know the answer. What I know is if the input is bounded and if that results in an unbounded output, the system is unstable. Now, what if the input is unbounded, right? So, something strange happens here. Okay, so say I take a system with transfer function of this form, right? It has again a right half 0, and I subject it to an unbounded signal e power t, unbounded input signal. Okay. So, what would we typically expect, that we would expect that the response of the system would also be unbounded. Now, the number 1 is a 0 of the system, which means g of 1 is equal to 0. Then the response of the system, surprisingly, is not only bounded, but it also converges to 0, right? You can just see with the plot. Okay, so it is again starts from 0, e power minus t is the input, and I just come back to 0. Okay. So this is one strange thing. So what we had left out while discussing about stability is what about unbounded inputs? Well, unbounded inputs could also result in bounded outputs in under certain conditions here. But the system is naturally stable because the poles of the system are always on the left half plane. Okay. Now, some more strange phenomena. So after we discussed about what we called as the blocking effects of zeros, that we see something strange happening to what we had learnt in the earlier 9 modules, right? If input is a sinusoid, output is also a sinusoid. Well, no, there is something strange happening here. Input is unbounded, output might also be unbounded. No, something strange is happening here, that output actually is bounded, right? Okay. Now, there is something called, well, initial undershoot, right? So we'll analyze some of these examples here. So let me take a step response to a signal which looks like this, and again it has an unstable 0, if I may call it so, or a 0 in the right half plane. So what you see here is, starting from 0, if I were to track a step, I am actually moving in the correct direction. Okay, I move in the correct direction, but here something happens and I just go back to 0. Okay, so after some time passes, the system reverses and moves in the wrong direction, right? So if this was a plan, say maybe I hire a new CEO in my company, which was not doing very good until yesterday. There is a big positive sentiment in the market, the stock prices go up. After a few months, I realized that this was not a good decision to have this new CEO. Nothing changes in my profits or even my turnover, and I see, well, that the response actually goes down, right? So this could be encountered in several situations, an inappropriate plan, right? Even sometimes you elect a new government, right, which promises a lot during the election campaign. The market sentiment is high, everybody is very happy, stock prices go up, but after a few months it's all the same story again, and it again goes back to 0. Okay. Now, some other things could also happen. Here what is happening, I take a decision and the initial trends look very nice, but then after a while I realize that I made a mistake by hiring this new CEO, or even hiring or even voting for a new government because of the trend that follows later on. Now here something else happens, right? So if I say again, I take the same transfer function with a negative sign here, and what I observe here is, okay, if I just start here and I just wait for a while and see what is happening here, I am actually tracking the step properly, okay, there is no error, nothing. But what is happening initially is I am actually going down. I go down and then I start rising after some time. For example, if you look at the demonetization, the initial trends suggested that the productivity in the market was going down. Some analysts suggest that maybe the government would say it actually went from 0 to 1 instantly, but we are not looking at what the politicians say, but just the initial trends would suggest that because of demonetization there was a cash crunch, and we are somewhere here now, right, at this stage as we are recording this lecture. But what we hope, or the government hopes, is that we will go somewhere here. Eventually we will start rising, possibly rise to higher levels. But however, the opposition thinks that we'll just go down and down until the next election, when the opposition gets elected, and then the upward trend will start moving. Okay, so we'll not do the analysis of what the politics or the economists say, but a decision sometimes leads to the movement in the wrong direction, and eventually it might just pick up. So a response of this departs in the non-asymptotic direction. What is asymptotic direction? That I want to track this number 1, and this results in an initial error growth. So, the error, well, if I just start at t equal to 0 plus, it will just be about 0, but the error is actually growing, but after a while you see that it's decreasing. So, the step response of an asymptotically stable strictly transfer function, strictly proper, right? This is a little important. For proper transfer functions, something else might happen, and we will not worry about that at the moment. So, the observation is that the step response of an asymptotically stable strictly proper transfer function exhibits an initial undershoot if and only if it has an odd number of positive zeros. Again, we will not really do the proof of this one, but if there are odd numbers of positive zeros, we expect a trend like this. Okay. Now, what happens when I have an even number of zeros? So, you have s minus 1 and s minus 1. The response initially moves into the correct direction, right. So, you say after a while, and then I actually goes down, and again I am actually picking up, right. So, however, the system reverses here, it goes negative and again reverses here. So, the step response of a system with multiple positive zeros can exhibit multiple reverses in the direction. Again, I will not do the proof of this, right. It's just, we'll just observe few things what are happening, and okay, these are things which would not be done in standard control syllabus or in the GATE or even undergrad text, but these are actually a little bit of fun things to know. What are the things, nice things or even the bad things that could happen with non-minimum phase zeros. Okay, so what we see in these plots is that, well, there is a zero crossing. Ideally, what we would expect, well, if it is say underdamped or critically damped system, where the response goes like this. If it is a underdamped, so if it's overdamped or critically damped, this is the case. If it is underdamped, then I expect some oscillatory behavior, overshoot, and so on. Here I experience something else, right? I start here, and I go here. I again cross the zero once. I come here, I again cross the zero once more. Here I am crossing the zero once. I go down, I cross the zero here. Okay. So, when do these zero crossings happen, and how many of them happen? And what is the evidence that this actually happens? So, if an asymptotically stable transfer function possesses at least one positive zero, then the step response undergoes at least one zero crossing. So, if there is at least one zero sitting on the right half plane, there will be at least one time where the plot will cross 0 or when the response will cross 0. Okay, so how do we verify this? Let us say the number z denotes a positive 0, okay, of the asymptotically stable transfer function. This is important, right? Unstable systems, there is nothing we could analyze. The Laplace transform of the output for, and if I am just looking at a step, is y of s is g of s over s, and what happens at s equal to z, which is the positive 0? Well, I have y of s is g of z over z, g of z equal to 0, it follows that y of z equal to 0. And what is y of z? Now, this y of s is the Laplace transform coming from this formula. This is simple formula, e power minus st ft dt, right? I am just substituting z for s, and what I see here is this value of the exponent is positive all the time, right? This guy, e power minus zt, and what could only go to 0 is y of t, and therefore we say that there is actually a zero crossing when this happens, at y of s or g of z going to 0, and actually y of z going to 0 actually means something like this, and because e of z is always positive, y of z should go to 0 sometime. Okay, that is what this argument says. Since e of z is positive for all times, it follows that y of t must cross 0 somewhere in this interval, right? Okay, now this is important here, right? Note that this only depends on the positive number z. It does not depend on either the poles or the remaining of zeros. Just this guy is what is causing it to cross 0. So, at least one zero crossing occurs if the transfer function is proper and has at least one zero on the right half plane. Okay, now if there are more, then you will have multiple reversal of directions in such a way that the step response must possess at least 2 direction reversals if it has a non-zero even number of positive zeros. So, I am just writing down this statement which I observed here. I have two direction reversals and 2 times I cross 0, one is here and one is here. Okay. And the number of zero crossings is equal to the number of positive zeros. This is only for strictly proper transfer functions, and these are also many of these are just by observations, and I think this statement has still not been proved mathematically. Okay, now zero crossings, are they only with positive zeros? One may ask, what happens when my roots are imaginary or the zeros on the right half plane are complex conjugate? Well, it still has 2 zero crossings, right. So, things also extend to the case when we have poles which are not only positive, but also right half zeros which are not only positive, but also complex conjugate. Again, these are just a little examples. Okay, so what we have done so far is in this module, which is possibly the shortest of all modules, is to analyze the role of zeros from a different perspective, not just looking at a lead compensator or a derivative control action. We are seeing what happens when the zeros are on the right. There are several other facets of this particular topic, but we will just restrict to just what we need, just the basic information of what we need. And why were we interested in this? Because we were interested in doing the experimental determination of transfer functions via the Bode plots, via the magnitude of the Bode plot, magnitude plot of the Bode thing. So, in that case there was a unique correspondence between the transfer function and the Bode plot if and only if the system was a minimum phase. So, what we saw here was minimum phase systems and then the definition of non-minimum phase, and how the concept of minimum phase systems was crucial in the experimental determination of transfer functions, and we saw the effect of right half zeros on the system response, things like the unstable pole zero cancellations, blocking effects and so on. So, all this material for this I just referred directly to this paper. It is a very beautiful paper to read. If you have time, you can. There are several other examples of the inverted pendulum, some examples related to even servo systems and so on, and also good examples of day-to-day life examples, where when you say I am riding a bicycle and I want to turn to the left, a typical answer, if you ask anybody how would you turn your bicycle to the left, he would think it's a stupid question to ask, that you are just going and then you just do turn left all of a sudden. But that is not true, right? So, what you do is you first turn a bit initially to the right, create an angle so that then you turn to the left. Just observe this when you are next time on a bicycle, right? So, these are all several phenomena which are not very obvious to us, but they, if you go a little bit detailed observation, you observe the effects of what we actually saw in this lecture in terms of plots. Okay, so in the next module, what we would do is, I mean, most people are interested in learning some practical applications. Applications could be several, right? From process industry, a very popular application is robotics, and people say, well, all robotics is just buy a robot, get a microcontroller, program it, and do. So, we will spend an entire module on some applications. So, a colleague of mine, Dr. Vishwanath, will be handling that module. He is very experienced in, he has a rich experience in industry. He was involved in the development of the LCA, which is now called the Tejas. He worked with Honeywell for a very long time, so he has good experience in practical aspects of control, and he will teach you few things about inertial measurements and sensors and so on. So, I hope that will be a little more interesting. Again, this will not be a part of the standard control curriculum for either GATE or even while crediting a normal course in the university. But nevertheless, we thought it will be a little more interesting to add a bit of practical aspects. We cannot add all the possible applications, but at least one application where you can directly see what you are learning and how to apply that in real life. And I will see you back again during the last lecture in the module 12 on state space analysis. Thank you.